Hey guys, welcome back. So let's get started into our intro of the thermodynamics. So I'm going to go ahead and share again so that you guys can see what I'm looking at. We're going to get into our intro of thermodynamics. So thermodynamics is the scientific study of the interconversion of heat and other forms of energy. That's what that means. We study the state of a system. So we're looking at a system. We are looking at its state. Its state includes things like its composition, how much energy it has, what temperature it's at, its pressure, its volume, things that can be used to describe that system. So anything that we can measure about a particular system is one of its properties. Okay. One of the things that we talk about in terms of describing properties is something called the state function. Now, state functions are properties that are used to determine the state of a system, regardless of how I got to that state. Okay, so there are things that matter how I got there. So like work, when I talk about work, it depends on what kind of process I use to get between point A and point B to determine how much work there was. However, if I talk about temperature, all that matters is where I start and where I end. It doesn't matter how I got between the two. So that's something called a state function. They are only dependent on the initial and the final states. State functions that we've talked about so far: volume, temperature, pressure, energy. Those are 4. Okay. Things like work that is not something that we're talking about for state functions. Okay. You may get asked to define a state function. You may get asked if something is a state function. Is it dependent on the path or not? You may get asked, give me a couple of things that are state functions. And you might get asked like what thermodynamics is, like a definition for thermo. So there's that. Now, when we talk about thermodynamics, there are laws that are involved in thermodynamics. And so we're going to have to talk about a couple of them. Here, we're going to talk about the first law of thermodynamics. Energy can be converted from one form to another, but not created or destroyed. Now, energy has 2 main components that we consider. There's the kinetic energy, the molecular motion and movement of electrons and molecules, and then the potential energy, which are the attractive interactions between electrons and nuclei, and repulsive interactions between nuclei and electrons, and between individual molecules. So there are attractions and repulsions that happen at the molecular level that we need to consider. That's part of that potential energy. Okay. Now, measurement of all forms of energy is extremely difficult to do. Very, very, very hard. But changes in energy can be determined experimentally. So we can say, okay, I don't know exactly what the energy is here, but I can say, here's where it started, here's where it ended, so I can look at that. That potential energy, U, is our measure of these things. Okay, so the U of the system is always equal to the negative U of the surroundings. So the potential energy change in the system is equal in size, but opposite in sign to the change in the universe. So if my potential energy goes up in my system, then the potential energy in the universe has to go down. That kind of relationship exists. If a system goes from high potential energy to low potential energy, like a stone falling off a cliff, then the surroundings gain that energy that was given off by the stone. It can be in a different form. It's not necessarily in the same kind of form that we were talking about, okay? Now, that's great, and that's awesome, but that's really hard to measure. So we're more interested in what happens to the system, not what happens to the surroundings, but what happens to the system. So let's see what that looks like. In that case, delta U, the change in that and potential energy in that system, is equal to Q plus W, where Q is the heat exchange between the system and the surroundings, and W is the work done by or to the system. Okay. So heat and work, and that defines our potential energy. Go, that's fun. Now, the thermodynamics of our system. So there's the heat, transfer of thermal energy between the system and the surroundings. This is not a state function. It depends on the initial state, the final state, and the path taken between the initial and final states. Our sign conventions. Heat absorbed by the system is positive. Heat given off by the system is negative, because we're looking at it from the perspective of the system. Okay, so that's why we have those sign conventions. The change in potential energy, U, is equal to the heat and the work. So delta U equals Q plus W. We just talked about this. So that heat, Q, and W work. Work is energy transfer that is used to do something other than change the temperature. This is also not a state function. So it depends on the initial state, the final state, and the path taken between the initial and final states. Our sign conventions for work. Work done on the system by the surroundings is positive. Work done by the system on the surroundings is negative because that work is given off. Okay, so from the perspective of the system, again, there are many types of work that we can look at. There's mechanical work, thinking physics, dropping, moving, that kind of stuff. Electrical work, such as redox reactions, that is a form of electrical work. And surface work, things like intermolecular forces. So the surface tension at the top of a liquid is because there are lots of molecules that are all pulling in together, right? Their intermolecular interactions are all pulling them down, and that creates a surface tension. The more interactions we have between those molecules, the more they pull down. That gives us a higher surface tension. That's why water has such a high surface tension, because there's the interaction of the dipole-dipoles, there's the interaction of the hydrogen bonding. All of that stuff pulls in and gives us a very high surface tension there. We can also talk about mechanical work. So expansion and compression of gases is typically what we're talking about with that. And so the work in that case is equal to the negative of the pressure times change in volume. Okay, so that change in volume is important because it affects our pressure. So that's the thermodynamics of our system. Ta-da. Questions, comments, problems on that? Hopefully not. But we're going to come back in just a minute and we'll talk about enthalpy. So again, if you have any questions about what we've covered so far, and again, really boring, really definition-based, that's what we're talking about there. Awesome. I will talk to you in a few minutes. Thanks, guys.